Okay, so graph structures are all around us. Probably all of you are familiar with graphs, and the graphs can be anything. They can be molecules with their atoms connected in the form of a graph, or social networks, social media with people as nodes, and we can have knowledge graphs and 3D meshes, and all of these structures have something in common, and they can be defined in the form of a graph. For us in the computer vision community, graphs in the form of thin graphs and also meshes, and in the general, like graphs for vision are more important. So most of the talks today will be about thin graphs, but also because nowadays the topic of vision language models has been more prominent. There will be also some works about using LLMs for scene graphs and etc. So scene graphs, before we know them in the computer vision world, were somehow used in the industry of graphics and animation. If you look at these animations, you can see that they follow the same pattern, and we can say that these two have the same scene graph, but with different appearances, and these have been in 1970s or even earlier done by Pixar, and they define the universal scene description that, as you can see, these are the same, they belong to the same scene. They have different visual appearances, but the same description. And scene graphs, as we know them nowadays, were first introduced in 2015 by Johnson et al. And later, the visual genome dataset was released, which is one of the main benchmarks in scene graphs. Later, 3D scene graphs and also semantic scene graphs for different applications were introduced. Also, some of these were by Archer, Federico Tombari, and Nasser Nawab. And later, which is also more relevant these days because video models are more popular. There were some data sets for temporal scene graphs, such as action genome and home action genome, that model the videos with scene graphs. And as you can see, the number of publications on scene graphs has increased in the since the early advent of this topic, and it's still increasing. And there are still a lot of challenges with scene graphs, such as panoptic scene graph generation, image generation and manipulation with scene graphs, using knowledge graphs and LLMs for also for scene graphs and scene graph generation from videos. Today we have the a combination of talks by our invited speakers and also the talks by you, and also the talks by the people who had their papers accepted. We started with the opening remarks with the oral session number 1, which will have 4 papers, then 3 papers as a spotlight presentation. Then we will have our keynote speaker, Dr. Krishnamurti, and then we will have a coffee break with the poster session and the second oral session, and 2 other keynote speakers, the Professor Volker Tresp and Brian Perozzi. And in the end, we will have a small conclusion. And here I would like to also thank my co-organizers, Professor Esana Adeli, which is there in person, and I think Iro and Federico will also be there. And now we can start with the first oral session.
Awesome. Thank you. Thank you, Azadeh. So for the first oral session, the 4 presenters, do we have the first presenters segment anything for road network graph extraction, Congrui? No, or online? All right, so we'll probably either skip them or wait until the end of the session. The second speaker is Flex. Are they online? Or do we want to move on?
I can play the video for their talk.
Let's go with the second presentation, and then
Are you also online for the Q&A?
Okay. The first presenter is here.
Okay, then we can start.
Okay, I just need to make sure screen is shared over Zoom. Zoom. I think I need to share screen, Azada. Have you stopped?
Yeah, I guess I just made you co-host.
Okay. The thing is, I do not see the. Okay. Where is the share screen button of Zoom? Screen is on the other side now. Okay. I found it. Desktop 2. And then. So, 10 minutes.
Can everybody hear me? Is this normal?
Maybe.
Yes.
Okay.
So good morning, everyone. My name is Song Rui, and today I will present our work named Segment Anything Model for Road Network Graph Extraction. Our code has been released. You can find it by searching the title. So the problem we are trying to address here is to extract road network graphs from an image, an aerial image that might be representing a large city region. We want to predict the vectorized road network graph represented by vertices and edges. The vertices might be representing the intersections and key points. The edges could be representing the road segments. This can be seen somewhat as a special type of scene graph prediction if you see the vertices as the entities and the edges as their relationships. So this type of graphs has actually many applications. Say autonomous vehicles could be utilizing them for route planning, and they are the foundation of navigation maps such as Apple Maps. And also creating this kind of large graphs is kind of expensive if done fully by manual labor. So like it is under active research for automatic and accurate methods to automatically create them. So the segment anything model, we are actually trying to incorporate segment anything model to this task in this work. So this is actually a foundational vision model released in 2023. It is trained for prompt-guided instance segmentation, and it is extremely good at this task, showing extraordinary accuracy and impressive zero-shot generalization capabilities. This is essentially a large visual transformer trained on millions of images and billions of masks, which is the root of its capabilities. So since its release, there has been a lot of applications of the segment anything model. For example, object detection, medical image analysis, and remote sensing, and even visual tracking. However, most of these applications are mostly still various types of semantic segmentation tasks. And how to leverage for predicting more structured objects, like a graph itself, has received less attention. And in this work, we'll try to answer the question whether segment anything model could help the task of predicting road network graphs and how well it can do it. So some prior works on the topic of predicting road network graphs. These works can be roughly divided into two categories. The first one is segmentation-based method, which is basically treating the task as pixel-wise classification, saying whether this pixel belongs to the road or not. And many earlier works actually just stop there and call it a day. And some follow-up works will use post-processing heuristics for vectorization to get the vectorized graph. These methods are quite simple and straightforward, and they can be made efficient by parallelization. And also, like the volumetric representation of the dense semantic segmentation mask naturally handles extremely complex shapes. However, like these heuristics could be their bottleneck for performance, and also like they are quite complex and brittle, and it is actually quite ill-formed to deduce the vectorized graph from the dense semantic segmentation mask. There are no universal heuristics that works for all cases. The other category is actually called graph-based methods. So this type directly predicts the graph structures from the net. They usually apply techniques like the transformer for object detection called DITR, and also like autoregressive methods to iteratively construct the graph incrementally. So the pros of this type of method is that they are somewhat more end-to-end. There are less handcrafted rules to help you get what you want. However, like my finding is that they scale quite poorly to very large regions and very large graphs. For example, the DITR really cannot detect more than a few dozen objects at once. And also these autoregressive methods, they have to build graphs step by step, token by token. They depend on the inference results of the previous steps. So it's kind of hard to parallelize, making them slow. So our method, it kind of has the benefits of the both categories while trying to overcome the shortcomings of both. It directly predicts the graph structure, the nodes and vertices. So the overall framework can be seen as 3 stages. First one is the encoding stage. Second one is geometry prediction, and third one is topology prediction. The geometry or the graph vertices are handled by dense semantic segmentation. We first predict the masks and then use a simple non-maximum suppression to extract the sparsified vertices. And then the edges between the vertices are predicted by a graph neural network, which just wires up the connection of these vertices. This defines the topology. So the encoding stage is basically we take the pre-trained the image encoder from the segment anything model. This is basically a plain VIT structure. It is a stack of transformer layers interleaving the windowed and global attention. There are no bells and whistles such as like a feature pyramid network, etc. So this encoder produces a feature map of the 1/16th of the size of the original feature map, of the original image, actually. So for the geometry prediction stage, it is extremely simple. It has a minimalist design because the geometry decoder is actually just a mask decoder composed of 4 transposed convolution layers to predict 2 dense binary masks corresponding to the rows and intersection points respectively. It predicts this from the feature map produced by the image encoder. And then after getting these masks, we apply so these masks are the dense masks. We want the sparse vertices. So we apply a no-maximum suppression process to basically keep the pixel of the highest score within a certain radius. So this gives us the sparsified vertices. So as shown in this image, you can notice those little yellow dots. So the geometry prediction, despite its simplicity, it is highly accurate. You can notice like these thin and complex structures in the dense urban areas. This is especially interesting because there are, as mentioned, no specific architecture design in the backbone network to really make this network good at these kind of structures. So the topology prediction stage, so what it does is basically after we get these vertices, we go over each of them and see whether find its like close neighbors within a certain radius and see whether it is connected with all these neighbors. So the way it is done is basically for all these vertices, we extract their features from the image feature map through bilinear sampling. That makes the feature of the vertices. And then for each pair of source and target, we concatenate their vertex features and also their relative offsets. This makes up the feature vector of the edge. So all the feature vector of the candidate edges within this circle are passed through a graph neural network, which is actually just 3 self-attention layers, because attention is apparently all you need. And so eventually they predict whether these edges are actually connected. So the ground truth label is gained in this way. You can see it as starting a BFS search on the ground truth graph from the source node, and the search will stop whenever it hits another node, or like it goes out of the range. So all the nodes are hit by the search are considered connected, the others are not. And during training, this decoder uses teacher forcing, meaning it takes the vertices that are the noised version from the ground truth instead of the predicted ones. So the training setup is also actually quite simple. Like I will just skip this. You can refer to the paper. There are no bells and whistles. All the loss terms are just plain BCE loss, no focal loss, no that kind of stuff. Training is quite fast. It takes about 1 hour on one RTX 4090 GPU. And also worth noting is that our method can use sliding window inference to handle large regions. So basically what this means is that both geometry and topology can be inferred independently first for all the individual windows, and then they can all be aggregated together to refine the quality. I will skip the dataset section. You can find that in the paper. So in conclusion, the results is that our method, despite its simplicity, it performs in terms of accuracy on par with the more complex recent state-of-the-arts, while it is actually an order of magnitude faster due to that it doesn't have this complex heuristics, and it's very easy to parallelize. And you can get even more speed up by sparsifying the sliding window inference. So you can find more ablation study in our paper. But in conclusion, we demonstrate the power of the segment anything model, a foundational vision model, on the task of road network graph extraction. It reaches the state-of-the-art accuracy with a much simpler minimalist design while being much faster. And we hope this work provides additional insights into leveraging foundational models for scene graphs and prediction and graph representation learning. Again, if you're interested, scan the QR code, and thank you for your time.
Thank you. Okay. If there are any questions, we do have time for questions if anybody does have any. Otherwise, we can go to it. Go ahead.
Can you quickly, the sliding window method you mentioned, you provide a little bit more detail on that?
Sure. So the where do I have the? So what happens is that there are two passes. In the first pass, the mask for each. So basically, we have these individual sliding windows. In the first pass, the masks for each window are predicted in parallel. So you have these individual masks. They are aggregated together in a global manner, so you can vote towards the large image. And in the meantime, when predicting the mask, we also cache the image features for each window. So after you get this global mask, you can apply the same process to get the global vertices. And then like the topology decoder goes over each window. It first predicts the edges within each window. And since now the vertices are global, you can actually vote towards the global vertex for the edge probability. So now that, yes, so basically they can all be aggregated together for quality refinement.
Perfect.
Couple of quick questions. How does it handle curves? So question one, how does it handle curves? These are not really straight lines.
So like first this mask, they can apparently handle the curves. So like the NMS process, it basically like turns the dense pixels into like a set of like vertices. Like you can control like the distance between these vertices. So I make it small enough so that it has the sufficient resolution to handle curves.
How would it train though? Because there's no right way to create vertices.
Exactly. That's why the vertices are not the ground truth labels. The ground truth label is the mask, and the vertex is just whatever you get after the NMS from the mask.
Second question: how do you handle roads that don't intersect, but they are one on top of each other?
That's a great question. So that's actually quite one of the limits of the current work. But like luckily, like well, in most cases, actually, it can be handled by as long as you don't have one vertex that happens to be at the exact location that two layers of rows like intersect with each other, like the topology decoder has a good chance of predicting the correct edges that overlaps each other. But like if you actually have to get a vertex there, you are out of luck, then it doesn't handle it.
Thank you.
Perfect. Thank you very much. Perfect.
Thank
So,
you.
great. Yes. For the second presentation, the presenter is online, and we are going to see the video first, and then
Hello everyone, thank you for being here today. My name is Zizhou, and I am excited to present our work, eFlex, Efficient and Flexible Pipeline for Spatio-temporal Trajectory Graph Modeling and Representation Learning. With the rise of GPS and location-based services, the amount of trajectory data is growing rapidly. This data is valuable, but challenging to analyze. We need efficient and accurate methods to model it and gain useful insights. Graph modeling is an effective way to capture the spatial and temporal dependencies in trajectory data. Our goal with eFlex is to provide an efficient and flexible solution for trajectory graph modeling and representation learning. And we offer two models, eFlex-B, which is optimized for speed, and eFlex-L, which focuses on achieving high accuracy. Spatio-temporal trajectory modeling involves various approaches. Traditional methods, such as basic statistical and heuristic techniques, often struggle with large datasets and fail to capture complex patterns. To address these issues, graph-based methods have been developed. These methods convert trajectory data into graphs, like row network graphs and activity graphs, but they come with high computational cost and complexity. To further enhance representation learning, graph neural networks, or GNNs, are utilized. GNNs effectively capture spatial and temporal dependencies by learning embeddings from graph structures. However, they require significant computational resource and sometimes lack flexibility. To address these challenges, we introduce eFlex, an efficient and flexible pipeline with a dual model approach, addressing both the need for speed and the need for accuracy in trajectory data modeling. eFlex constructs graph directly from raw trajectory data, converting the trajectory representation learning problem into a task of graph embedding learning. Formally, assume T as a set of n trajectories. Each vertex Vi represents each trajectory Ti. Originally, all trajectories are represented as lists of longitude and latitude. The weighted adjacency matrix is computed based on the relative distance between each trajectories. To capture both global and local information, we compute multiple adjacency matrices based on different k values and then fuse them using attention mechanism. For a set of k, we can have a set of weighted adjacent matrices in multiscale. These matrices are then stacked and passed through a sequence of learnable linear transformations to compute the attention weights W. The final fused adjacency matrix, S prime, is shown here. The fusion operation allows the model to leverage features dynamically across multiple scales, keeping the original information as much as possible. Now we have converted the massive original data to a large graph. To further reduce the dimensionality of the data, the eFlex pipeline has a graph representation learning module, which uses a lightweight graph convolutional network to generate accurate graph embeddings. Formally, given FB as node features and S prime as the adjacency matrix, the GCN model M can be represented as this formula, where W theta and delta theta refer to the learnable weights and the bias parameter within the GCN. The output of the model indicated as EM theta is the learned embedding of n trajectories, each as 1 times D embedding vector, where D is the preset embedding dimension. To instruct the model to generate accurate graph embeddings, we employ cosine similarity distance as a loss function. Here, GT indicates the ground truth by computing Euclidean distance between every two trajectories in the dataset. Benefiting from the generalized and flexible pipeline framework, eFlex offers two versions, eFlex Base and eFlex Large, with different models employed in the graph representation learning module. eFlex B uses the lightweight GCN for fast processing, while eFlex L uses Node2Vec for high accuracy. These two versions provide the eFlex pipeline with the ability to handle diverse application needs. To evaluate our pipeline's performance, we conduct extensive experiments on two commonly used trajectory datasets collected from the real-world data points: Portil, which contains taxi trajectories, and GeoLife, which includes GPS trajectories of virus users. Considering the complexity and variability observed in the real-world traffic trajectories, the Portil and GeoLife assets are ideal for evaluating model performances. To conduct objective evaluation, we evaluate the model performance on the top-end similarity search task problem. Specifically, given a query trajectory, the model outputs the top-end similar trajectory based on the embedding under a certain distance function. The higher similarity search accuracy indicates the more accurate learned embeddings of the original trajectory dataset by the model. The distance function we use here includes Hausdorff, Frechette, and DTW. Following the standard evaluation procedure, two evaluation metrics are involved. The first one is hitting ratio, which is HR at 10 and HR at 50. The second one is recall, which is R10 at 50. Also, we compare the results with both non-learning models, including PCA, SVD, and MDS, and state-of-the-art machine learning models, including Siamese, NEU Trage, and T3S. This table shows the graph representation learning performance. Both of our solutions, eFlex B and eFlex L, outperform existing models and achieve state-of-the-art results. Under the Hausdorff distance metric, eFlex B achieves a hitting ratio and recall of 55.10%, 64.92%, and 98.17%. eFlex L performs even better, with 56.51%, 71.26%, and 99.84%. eFlex B and eFlex L both show significant improvement over non-learning and learning-based methods, leading in hitting ratio and recall. Similar results are observed in the GeoLife dataset. Our model's multi-scale KNN graph construction and fusion help preserve important global and local features. Using the graph convolutional network allows our model to converge effectively, capturing graph-level representations and significantly improving performances. We also compared the efficiency of eFlex B and eFlex L on the Portil and GeoLife dataset using the same CPU environment. We used the recall as the accuracy metric and measured the time cost under three distance functions. The results show that eFlex B achieves competitive accuracy while significantly reducing the time cost. Thanks to our lightweight GCN design, eFlex B captures graph structure patterns effectively and improves training speed. eFlex B, being an innovative design, highlights our contributions to learning graph representations on spatio-temporal data. Its accuracy and speed make it suitable for lightweight platforms like mobile phones, wearable devices, and autonomous driving. For applications that don't require real-time modeling, such as environmental monitoring, eFlex L is ideal due to its high accuracy. This figure shows the trajectory query results. Using the Portil dataset, given a query trajectory, our model finds the top three similar trajectories based on the learned embeddings. The results closely match the ground truth, proving the effectiveness of eFlex. These results validate our approach of dimensionalizing spatio-temporal trajectories for graph construction, efficiently representing large datasets. eFlex also has practical applications, like finding alternative routes in navigation. We conducted ablation studies to verify key components of our model. First, our multi-scale KNN with attention outperforms other methods, providing more accurate learning. Second, multi-scale graph construction is better than single-scale, capturing both board and localized patterns. Third, increasing embedding dimensions from 16 to 1024 improves performance, making the representation space closer to the original data. This table shows the ablation studies on different loss terms, where cosine similarity distance outperforms L1 loss and MSE loss. Considering the ability of cosine similarity distance to ignore the effect of data sparsity and dimensionality, It is less sensitive to outliers and variations in the magnitude of the spatio-temporal graph representation learning. This indicates it to be the ideal loss term for stable pipeline training. In conclusion, eFlex offers a novel and efficient approach to spatio-temporal trajectory graph modeling and representation learning. Our pipeline significantly improves both speed and accuracy, making it suitable for a wide range of applications. In future work, we aim to further optimize eFlex for greater scalability and real-time applications, such as traffic management and environmental monitoring. We're also exploring the integration of large language models to enhance the semantic understanding of spatio-temporal data, which could improve predictive accuracy and analytical depth. That's everything for my presentation. Thank you for listening.
Thank you. I believe we have the speaker online, and if there are any questions, we do have the speaker online, right?
Yes, Z is here.
Okay.
Hi, everyone. My voice is not actually like in the video. I speed it a little bit so to save some time.
Okay, yes. All right, so if there are any questions here or over Zoom, please let us know. Yeah, I think this is a little bit of a challenging setup because if you want to ask a question, you probably should step here. So that's why nobody's asking question. All right. So then maybe we can move on to the next presenter. Do we have Flowcode D papers author here? I think they did confirm for the presentation, right? Because I have the yes, the plan was to do the presentation. Maybe we can do the switch and the last paper in this session, the oral session. We do have
VideoSAGE.
yes, VideoSAGE. We have the speaker here. Let me make sure I do the right setup for screen sharing. Just blocking the view of the previous one. Okay, we can start.
Thank you. VideoSAGE, video summarization with graph representation learning, of course. Good morning, my name is Jose Rojas, and I work for Intel Flex. And I did this project in collaboration with Suvarna Tripathi from Intel Labs. Okay, AI everywhere is like the new Intel's mantra, and that's me as software developer talking to researchers at Intel Labs. So to really have AI everywhere, we need to have more efficient and yet more effective models that can be run on our mobile devices and laptops. And the problem is that in general, current video models works on short video clips. So we need to have, and that's due to computational memory bottlenecks, right? So we need to have models that can be run on longer videos, or at least that can be run on the same videos but faster. So if at the end, if we are able to achieve more efficient models, then that means we are able to run those models in our computers on the edge, and we will be able to keep our data local. That's more security. That's also more power efficiency, and that's also reduced response time. So how can we achieve these kind of models? We are lucky enough we have Gravity. Gravity is an open source framework from Intel Labs. So you can, with this framework, you can take videos, and sometimes you can also do audio and text. So you can build graph representations with the spatio-temporal data. And then with this graph, you can do interesting applications like active speaker detection, action segmentation, or action localization. Some of the applications are not implemented yet, but now we also have the summarization. So how can you use Gravity to build this representation? It is easy. So we took two popular data sets on video summarization, SUNME and TVSUN. These data sets already come with features starting with Google Net model, and they already come in segmented with kernel temporal segmentation.
Yeah, it's the microphone, whatever it is.
Oh. So you did something here last time.
That's for the speaker. That's just a speaker.
Mm. Okay.
Turn it off and on again.
So basically what you have to do is to take and define a node for every frame on the video. And then the embeddings of those nodes are going to be the features from the Google Net network. Then you are going to connect those nodes with a limited number of adjacent nodes by some temporal distance. That way you enforce some sparsity in the model, and having this sparsity is good so you can avoid hidden computational or memory bottlenecks. So then what you need to do is to define the task as a binary node specification problem, where you have to say which frame is important, which one is not, which one is worth going to the summary, and which one shouldn't go. At the end, you are going to have importance score for every frame, so you calculate an average for every segment, and then you can use the NAXAP algorithm to choose the segments that are going to be in the summary in order to maximize the total importance of the summary video. And the summaries are going to be 50% the time of the length of the original video. So typically there are 3 evaluation metrics for video summarization. The first one is the F1 scores, and the second, the Kendall-Stahl Spearman-Rowe are correlation metrics. So it's been proven by Otani et al. That the correlation metrics are better for evaluation of these summarization tasks than the F1 score. However, many state-of-the-art is still using the F1 score. But as you can see, if you use pure random predictions, you can already get almost 55% score on the F1 score, which is pretty high and is close to the state-of-the-art. So Otani suggests to use the correlation metrics because that way you can get a 0 score with the Spearman tau. But on the other hand, if you use perfect predictions and really that's using the ground truth, you can see that you can only get up to 46 with the method from Otani. So we change it a little bit, the evaluation, in order to use the full range of the metric. So I'm going to explain a little bit here. The thing is that there are 15 to 20 user annotations on the dataset for each video, and Otani et al. Did this correlation metric to each of those user annotations and then average the results. That's why it kind of get penalized and not get to the one. But instead, we are using the ground truth to compare with in the correlation metrics, and we think that's a more typical evaluation approach of machine learning. So these are the effectiveness results. We were able to achieve 33% improvements on this correlation metric for the Sony dataset and 11% improvement for the TV Sony. And in terms of efficiency, so we're able to do it 5 times faster on inference times than the states they are, and using 3 times less memory. So getting it to be effective was good, and now getting it to be more efficient is even better. In terms of the qualitative results, assessing the videos just by looking at the summary is a bit difficult because it's subjective. We have a link in our poster, so you can, if you want to check more example videos with summaries. But I think one can definitely say that we achieved comparable results with the state of the art. On the other hand, we have the importance predictions on the right. In the middle, we have the ground truth. On top is our predictions from VideoSAGE. At the bottom, we have PGL soon, which is the state of the art for comparison. By the way, this specific example, this video got better exponent scores on PGL soon. But as you can see, our predictions resembles way better the ground truth importance scores. So that's another example why correlation metrics are better. So we got VideoSAGE, graph-based representation learning framework for video summarization. So we did experiments in 2 prevalent data sets for video summarization, Sony and TV Sony, achieving more efficiency and more effectiveness. And we also suggest and apply a more comprehensive evaluation approach for importance prediction. And if you want to check our repository for this application and other applications, you can scan the QR code. And for more details, you can also visit poster number 63. Thank you very much.
Perfect, thank you. Any questions? Maybe I actually had a very quick question. You talked about long video understanding using this type of approaches and using scene graphs in general. Any comments on, like, if you have very long videos, then you have a very tall scene graph, very big scene graph over time, then how this is handled, and then does your efficiency arguments still hold?
Well, not on this application, because these datasets have videos only to 5 to 10 minutes each. But I know there is another application for active speaker detection, I think, that they were way longer videos. So what they did was to split the videos in shorter clips, and then they will have a graph for those shorter clips and do the processing, and then they will like rejoin the results from each of the clips, if I'm not misunderstanding.
That's how a lot of downstream applications, and as you asked,
It would be great if you, since you have some audience on Zoom, so thank you.
Thank you, Azir. So if you can, scan the QR code, you will go to a toolbox called Gravity. That's from Intel Labs, open source toolbox that handles a long form video representation learning and serves many different applications. So far, we have enabled half a dozen applications. We plan to do more. And one particular example that Jose also mentioned, for example, active speaker detection. So in most of the other models, they are processing, let's say, 4 to 10 seconds at a time. Whereas with our sparse graph-based approach, we are doing it at 1 minute time scale. For some of the applications, it depends on the data set, the kind of videos that we are processing or dealing with. Sometimes it is needed to do the processing over short clips at a time, and then we do some sort of processing. Sometimes it's enough to do all the processing over the unfilmed videos. But so far, we are making our strides towards at least a minute or two, whereas the traditional transformer-based methods are able to look at 5 to 10 seconds at a time. Hope that answers your question.
Perfect. Yes, thank you very
Thank you.
much. Appreciate it. Any other questions or comments from the audience here or online? Trying to look at the schedule.
Maybe I can ask a quick question before. How do you handle if there are discrepancies between different shots? So if there is suddenly a change in the shot within the video?
Well, that's already handled by the datasets because these datasets come with, segmented using kernel temporal segmentation. So this method look into patterns in the video, like change in actions or color or other patterns to recognize the like big changes in the video, and then it defines the shots. So the dataset already comes with one.
So it's done during the pre-processing, is that?
Yeah, of the datasets.
Yeah.
That's right.
Thanks.
Thank you. Thank you. Let's thank the speaker again.
Thank you.
Just double checking, do we have a speaker?
Anand Handelwal?
Yes. We have Anand here. The paper flow code D, unbiased dynamic scene graph generation with temporal consistency and correlation debiasing. The assumption is
He's online. Anand, do you hear us? He has joined online, but the sound is not connected. Anand, do you hear us?
there is Zoom.
Yeah, sorry, I was on mute. Yeah, I'm able to hear you. Yeah.
Also,
You
are you
plan-
presenting online or?
Yes, I will be presenting online.
Okay.
Yeah. Hi everyone, I am Anand Khandelwal. I am an applied scientist in Microsoft, based out of India. Sorry for the delay in the presentation as per the timings. I will be presenting my paper titled Unbiased Dynamic Scene Graph Generation with Temporal Consistency and Correlation Debiasing. So this is a scene graph generation for videos, and I will be talking about the contributions which I have made in this using incorporating the temporal consistency using the flow-based network and the correlation debiasing. Next slide. We'll be discussing yeah we'll be discussing what exactly the introduction to the dynamic scene graph generation and the current state of the art and the limitations, then the proposed solution.
One quick note, there's a lot of background noise where you are. And is there a possibility that you can change?
Sure. Yes. Is it better now?
Yes.
Yes.
So we'll discuss the dynamic scene graph generation and what has been proposed in the current state of the art and what are the limitations. We'll then uh, discuss the proposed solution flow code and the technical approach we took to solve the current state of the art and the current limitations. We will then discuss the results and the performance, and finally we will discuss what we conclude as part of this whole exercise of doing the introducing the temporal consistency and correlation device. Next slide. Uh, so current in the dynamic scene graph generation, our focus is to represent the video in the form of a dynamic graph such that it can capture the temporal evolution between the objects. For example, you have a object one and object two, which can interact with other objects in a changing environment as the video passes by. For example, if the object one and object two has a relation in frame one, and then after frame n, the object one and object two are no longer related, and there's an object two and object three which is related along with some other objects as well. So we want to learn this temporal evolution the between the graphs, which is dynamic across the frames. So this is called a dynamic scene graph generation, and this is this has various applications like when we want to ask about the fine grained information into the video. It can help in the video question answering task, and if we can summarize the whole video in a form of a simple one liner statement, we can also do that by summarizing a graph, and that that can help in a video captioning. Along with that, we can assign some text to the video as well, so that it can help it in real time for the retrieval task as well. So there are some uh, challenges associated with it, that the dynamic relations and the temporal dynamic dimension uh, has an added complexity here. So so people have modeled this in a various ways related by transformer, where the input is the the number of objects which the object has a relation with across the temporal dimension, and then it tries to classify the predicates between these objects related with the object one, and try to learn the embeddings of the predicate and get the uh, get the get the different relations as the time passes by. In this way, it can learn the dynamic relations between the object. We'll approach this problem in a different manner in this uh, in our proposed method for dynamic scene graph generation. We'll discuss that in the next slide. So, as I said, the current state of the art has leverage transformer for learning the spatial temporal context. In the spatial temporal context, what they have done is, for a given object, they have collected all other objects on which for which the object is related, and they model this using the and he model this using the temporal by feeding all this to the transformer, and this learns the temporal context and along with the spatial context as well, that the all other objects which are in the same frame are being related to some other objects as well. So, and learning the predicate embeddings and classifying relations between the objects which are dynamically evaluated will eventually result in a spatio-temporal context being learned by the transformer model, and is able to is learn what how the relations modify over the time between a given set of objects. But there exists just a class imbalance issue in the dataset as well, that some relations are very frequently occurring between the objects, while some of them are very rare. So here, not only the temporal context need to be maintained, but we need to learn the rare predicates as well, so that we will be able to accurately generate the scene graph for a video. And hence the not the recall at the rate k metric, actually the mean recall at the rate k metric is a better evaluation metric here. So with the recall at the rate k metric, we will show how better how how better our algorithm is in terms of generating the scene graph, which is overall correct. But mean recall at the rate k will give us the uh, give us a sense that how it is performing across the across the different relations in an average manner. So it will give the equal weightage to the rare ones as well, and hence it is a better metric for the evaluation rather than just a recall at the rate k metric. So next slide. So our objective in this proposed method is to generate an unbiased dynamic scene graphs. And with unbiased, we mean that both the rare labels and the frequently occurring labels are being given the equal importance, and that can so that they can accurately represent the video content. We introduce the flow-aware temporal consistency. For example, in frame I and I plus 1, we calculate the flow between these two frames, and using the flow features being calculated, we are feeding these flow features to the transformer model to be able to classify whether that that object belongs to which category. In this way, we are being able to identify the changing nature of the object. For example, in frame I, the object is blur, and frame I plus 1, the object becomes a little bit more clear. Then, using the flow features, we have been able to identify what exactly the object category is, because in the scene graph generation in the previous state of the art, it has been identified that most of the object categories detected is self incorrect, and because of this mislabeling in the object categories, the labels detected are also incorrect, and hence we correct and hence we try to detect the correct category using the flow aware temporal consistency. Once the object categories has been detected, we then propose a correlation devising algorithm. Correlation
Sorry,
device.
Anant, we have 1 more minute. Could you please wrap up?
Yeah, sure. So with the correlate, and we then apply the correlation devising and the uncertainty aware weighted loss along with the label correlation based loss. So the whole idea is, with the correlation devising, we want to generate. We are accumulating the attention matrices that is uh, that is generated by the that is used by the transformer in generating the predicate embeddings, and we'll take a mean across the epochs of those attention matrices to devise the correlation matrices. And then finally we use a mixture logic network and the derived weights from that, using the epistemic and the aleatoric uncertainty. We then weight the loss so that the noisy data points are being weighted down and the correct data points are being only being learned. We also take a clue from the contrastive loss learned using, which is taken into account the label correlation. For example, if uh, object 1 and object 2 predicate has a correlation between an object 2 and object 3, has at least one correlation, we tries to learn the embeddings. We try to we, we treat them as positive pair in the contrastive learning, and others are the negative pairs using negative sampling. So our approach consists of then flow aware object detection and the relation, and using flow aware and the relation representing using the correlation devising, and then we classify the predicates using the uncertainty weighted classification laws with the name, even with the under the noisy data, even with under the presence of a noisy data, and use a label correlation based contrastive laws so that we can occur the commonly co-occurring labels. Yes, next slide. Our results outperform as high as 4.1% in terms of mean recall k, and there is an improvement in terms of recall k at the rate k as well, which shows that our method is not only been keeping the performance of the base labels which are already been improving, but is able to improve the rarely occurring labels as well, and hence resulting in an improvement in terms of mean recall at the rate k, and hence it can generate the unbiased dynamic scene graph. Will show the qualitative comparison in the paper as well, for comparing with other SOTA methods as well. And the task which we have learned is predicate classification. Yeah, and so this is threefold benefits of our method is the significant performance gain, bias mitigation, and it can adapt to different dynamic environments across the video and can generate the more accurate dynamic scene graph. Thanks.
Thank you. And for the interest of time, unfortunately, we are not able to go to question answers because we already lost a lot of time. Let's thank the speaker.
Sorry,
Great.
I spilled out the time. Thanks. Thanks,
No worries.
everyone.
Thank you. Okay, so we do have 3 spotlight presentations, and I would appreciate if the speakers can line up here. We have the first one would be
Open 3DSG.
Do we have the speakers of the other two spotlights presentations? We have one, and yours is going to be the touch. No, this is not you. The manga whisper, right? Okay. Do we have the touch up G speaker also in the room? Is that you? You're the second speaker. Just yes. Thank you. Just wanted to double check. So we have all of the speakers, and let's get started. So this is gonna be around 4 minutes of presentation, a couple of minutes of question answers. Stage is yours.
Thanks. Okay. I will present Open3D true open vocabulary 3D scene graph generation from point cloud with queryable objects and open set relationships. So the task of 3D scene graph generation is going from a point cloud representation to a graph-based representation where the nodes are the objects in the scene and the edges are the relationships between the objects. And usually methods use supervised learning to train this task on the most popular data set for about 20 object classes and 8 relationship classes. For a more fine-grained data set, it's about 160 object classes and 27 relationship classes. Of course, having like a more fine-grained label set improves the representational capabilities of your model. However, these labels are still set during training time or even during the annotation time of the data set, right? So we want to propose true open vocabulary 3D scene graph generation without supervised learning, where not only the objects are open vocabulary, but also the relationships, such that we can predict the most specific relationship for each object pair. Let's say CLIP was a very seminal work in the field of open vocabulary classification. CLIP trains an aligned vision and text encoder and uses the cosine similarity to predict the correct open vocabulary class. However, we find for compositional object concepts such as relationships, CLIP's representational knowledge just fails for this. For example, for this relationship between the guitar and the bed. So we cannot do what most open vocabulary 3D scene understanding methods do and just distill the CLIP knowledge into our model. So in detail, we want to train a graph neural network, which takes as input a point cloud and outputs a feature graph representation of the scene. And now we want to align this basically with 2D foundation models. Here for the node, we want to embed the object knowledge of OpenSeg into our graph using cosine similarity laws. And then at test time, we can just predict the open vocabulary class of the nodes by querying the line CLIP text encoder feature embeddings to get the open vocabulary classes. But for the relationship, this doesn't work, as we discussed already. So what we do instead, as you can see in the upper right corner, we go for vision language models which have an encoder-decoder structure with an LLM as the decoder, because we want to basically leverage the world and relationship knowledge embedded in the LLMs. So what we do is basically we cut the connection between the encoder, the vision encoder part, and the LLM decoder part. And then similarly to the objects, we basically use the vision encoder blip model to distill relationship features into the edge embeddings of our feature graph. And then in the final step from the 3D feature graph, we can then together with the already predicted object classes, the feature embedding of the relationship edge and a prompt like what's the relationship between these two objects, we can predict using the LLM, the open vocabulary relationship between the objects. So this actually works quite well for a given point cloud. I would highlight this relationship here between the TV and the wall, where our model predicts that it's mounted on the wall, which is very specific. Quantitatively, we can see that our scene graph conditioned LLM model definitely outperforms the 2D CLIP version for this by quite a large margin for both objects, predicates, and relationships. But we also see quite a large gap still to the supervised learning methods that were specifically trained for certain classes in the benchmark. But this is the same for all 3D open vocabulary scene understanding models. And we just aim to close this gap in the future. But because everything in our model is open vocabulary and the predictions are zero-shot, you can also do zero-shot applications that we didn't even train for. So for example, here we can query for each node a attribute that describes the appearance, shape, or size of the nodes. Or we can even like prompt affordances between objects. Like for example, could you lift object X from object Y? Here, for example, the LLM could say that the pillow you can lift definitely from the bed, but you cannot lift the bed from the floor because it is too heavy, of course. And this actually concludes my talk. This is actually a full CVPR paper, so you can also come to our poster on Thursday, but I'm also here to answer any questions.
Great presentation. Any questions from the audience?
Also on Zoom, if there are any questions.
There's one in the room.
We need some information data to adopt this structure.
So it is fully open vocabulary, but of course, so we train our model on indoor scenes. So the distillation part only happens on indoor scene. So there will be a bias towards indoor scenes, but generally you can adapt this to any kind of scenario without needing any labeled data.
So have you tried to use this model to conduct like 2D synchronous generation?
So we haven't done this. So this is focusing entirely on 3D synchronous prediction.
Perfect, yes.
What's the data set you benchmark?
So we benchmark on 3D SSG, but we train actually on ScanNet.
Amazing. Was there a question online or?
No, I was asking if there is any question.
Okay. Thank you very much. Again, thank you.
you.
Let's thank you. Our next presenter will be Jingju, right? Great. So improving feature representation through graph-centric fine-tuning.
Oh, hello everyone. I'm Jing. This is actually a SIG-IR paper. So we are doing Ketchup-G, improving feature representation through graph-centric fine-tuning. So in the task of recommendation systems, it has been like widely used in everyday lives, like e-commerce, content sharing, and social networking. So one of the key tasks for link prediction is to one of the key ways that we solve the recommendation system is to cast this as a link prediction task for feature-rich graphs. So for example, we gather the co-purchasing informations like given item A, which items tend to be bought together with item A. And the features will tend to be text descriptions, images, etc. So one of the key paradigms that we solve this problem is to use pre-trained models, such as BERT, to get its like feature encoder informations and then pass it through the graph neural networks. However, this approach actually is pitiful because, so for example, in this Amazon co-purchasing graph, every feature actually has pretty distinct feature representations. And if you pass this through a vision transformer, it will go towards like very different feature representations that actually does not really have any correlation with the graph structures. But they are often brought together. So this shows the pitfalls of this method paragraphs. And here, one of the key reasons why this paragraph does not work is these graph agnostic feature embeddings actually prevent suggestions from fully utilizing the correlations between graph structures and node features. And so the key research questions that we want to solve in this paper is how are we going to improve the node features from the pre-trained models, such as vision transformers, for downstream tasks such as link prediction. And to solve this problem, we propose the graph-centric fine-tuning method on the pre-trained models. So this method is basically agnostic to any type of pre-trained models, and we prove it's working for BERT, VIT, etc. And so the basic idea is to propose a metric called feature homophoby, where it decides whether fine-tuning is needed. And then if the feature homophoby score is less than 0.5, we would propose a graph-centric fine-tuning of the train transformers. And for more details, please see my poster. Thank you.
Thank you for the.
Great presentation. Any question online?
No.
Okay. Wait. Maybe in the room we have some questions. Any questions, any comments with the audience in the room? This was a great working presentation. I just wanted to see a quick question. How do you decide or differentiate that there is the need for fine-tuning or not? I mean, what's the criteria there?
Yeah, so we calculate a feature homophoby score, which basically calculates the Pearson correlation between two pairs of features over the connected edges. So if the over like an edge, the feature similarity score for two features is very high, it basically says so graph neural network is very likely to succeed in this task, so we don't really need to update its features. But if the correlation score is pretty low, probably due to like the different types of colors or stuff like that, then we will need to propose a graph-centric fine-tuning upon the edges, just to indicate that these two features are similar.
It's amazing. Yeah.
Thank you.
Thanks. All right, and the last presentation in this session before we go to a keynote speaker is presented by Raghav, right?
Yes, thank you. Hi, I'm Raghav. I'm a PhD student in the visual geometry group at the University of Oxford. I want to talk to you about making manga, which are Japanese comics, if you're not familiar with the term, how to make them more accessible to blind people. And this is from like a graph generation perspective. So really quickly, what the goal is. The idea is that if you have a page like this, a manga page like this, we want to go from there to something like this, right? Where we have got a dialogue transcript. There are three things we want to identify here. What's being said, who's saying it, and in what order is this being said. Now, let's unpack that a little bit, right? So if you've got a page like this, we want to obviously detect all the characters to figure out who's saying what. Then we want to figure out where all the text boxes are. We want to recognize the character. This is to say, like, these two girls are the same, those four boys are the same, everything else is like not really reappearing. We want to then match the text to the characters who are saying it. So this is the speaker diarization element of it. Once we've done all of that, then you can think about like, okay, let's just do OCR to get all the dialogues. And then you want to do some sort of ordering to decide what order things are set in. And for that, you kind of need to know where all the panels are. So a lot of things that you kind of need to do, right? Let's very, very quickly anchor ourselves to figure out why this is really challenging, right? So with manga, you can have characters that appear with changing viewpoints. So you can have back view, front view, top view, profile, side view. You can have characters that are drawn with varying fidelity. So same character could look very, very different depending on how the artist wants to render that and express emotions. You can have characters that are not actually humans, or characters that transform through magic. So one character can transform into another character. I mean, how do you even capture that? You can have resolution being a problem. So characters can be drawn very, very small and you want to detect those, which is tricky. Or with text, you can have, there's text, but there's no really character in that panel. There's no obvious who the speaker is unless you read and follow the story. Or you can have text where it's like an internal thought, not really a spoken dialogue. So here's the plan of action very, very quickly. We tackle it in a two-step process. First being detection and association. And here what I mean is, I want to detect the characters, text, and panels. And I want to associate the characters with other characters to say they are the same character, and text to character to say this text is said by this particular character. Once we've done that, we can do the transcript generation, which is just an OCR and ordering problem. I won't talk about the second part of it in this presentation in the interest of time, so let's just quickly look at detection and association. We formulate it as a graph generation problem. The idea being that the nodes in this graph that we're generating are the bounding boxes for character text panels, and the edges are the associations that I mentioned, character associations or text-character associations. Very quickly, this is what the architecture looks like. I'll just briefly skim over it, which is left to right, you have a high-resolution manga pages input, which is an RGB image. Goes through your standard CNN transformer encoder decoder. This is very similar to the detection transformer architecture, the Detra architecture, familiar with that. You get a bunch of object tokens that come out of the transformer, which are then processed by a bounding box head, which regresses the bounding box coordinates, and also a classification head, which says, this is a panel, text, character, or maybe background. Once we have that, this is like the node generation part of the graph. Then we want to generate the edges, right? What we do is we process these detected features in pairs. So we'll take like a text feature that we already know is a text box, and we'll take like a character feature, concatenate them along with the special token that I won't mention at all, feed it to an MLP and ask it a binary question. Is this text said by this character? And we'll output the number between 0 and 1, really like the confidence value. And that really gives us all the edges. And same thing for character edges. So take character tokens that have been detected, concatenate them along with like a crop embedding for each of them, and then feed it through a binary, like an MLP to ask a binary question, right? That's how we generate all the edges. I'll quickly go over some qualitative results. We do have some quantitative results in the number, and I'm not mentioning data at all, by the way, conveniently. So do come to the poster session. We can talk more about that. So given manga pages like this, it can detect all the panels, which I think is not unreasonable to do, and text, characters. Characters, by the way, are not limited to humans. So it can detect like dog-like creatures and all these other things. But interestingly, it can detect the character edges. It can cluster the characters on per page without really knowing the number of clusters. So it's not k-means clustering. We don't really know how many unique characters we have. But in this case, for example, the purple or pink lines that are showing connected components represent that white-haired character. On this right image, you can see like this girl front, like full body view, but then side view of her face and then back view, and it's matched all of that and said, okay, these are all the same character, and works very well. Beyond that, you can see in left image, you get partially visible body parts. It's saying like that hand is the same as that hand, which belongs to the white-haired character. Or you can have like this octopus-looking like creature, and I'll quickly skim over all of that. It also does text-to-character matching, as I said, which is the text-to-character edge is part of the problem. And then you can, I didn't talk about how you do ordering, which is also like a graph-based approach. We can talk about it later if you have any questions on that. And yeah, that's all I have to say on the topic. It is available in Hugging Face, so you can use it with like 2 lines of inference if you'd like to. And that's all I have to say. Thank you.
Thank you very much. Great presentation. Question?
Yes.
Ernest, I'll come to your poster, but just 2 quick questions.
Yes.
One, are you using relation former?
Yeah. So this is based off of relation form architecture. Yes. Yeah, correct. So there are 3 real data sets that kind of serve this purpose. There's an existing data set called Manga 1 and 9. That's, you can request that on you can request access to it. If you're like an academic and you want to do research for that, you can use that. And then we scrape like a large 2 million images completely unlabeled, and we talk a little bit about like how we use semi-supervised training for that. And then there's a smaller data set that we get humans to annotate, about 50,000 images that you train with large scale unlabeled data set, and then you fine tune with that data set. That's not, training is not open source, the testing is. It's just really copyright issues. So maybe we can talk about by email if you really want access to that, but I can't publicly release it because I'll just get in trouble.
Yeah, I would love to test mine.
Sounds good. Right. Anyone else? Okay, good. Thank you.
Amazing. Thank you. Awesome. Thanks, everyone. And I especially want to thank all of our speakers in this oral session 1, as well as very well done presentations in the spotlight presentation, the last 3 ones. Awesome. Azadeh?
Yes, so I would like to introduce our first speaker, Dr. Krishnamurthy. He is a postdoc at MIT working with Antonio Torralba and Josh Tannenbaum. He completed his PhD at Mila and the University of Montreal, and his research is on building computational world models to help embodied agents to perceive, reason about, and act in the physical world. He will give a talk about structured world modeling with 3D scene graphs. We are happy that you have accepted our invitation, and we look forward to the talk.
Thanks. Yeah, thanks for having me. And before I start, can anyone confirm that people can hear me both over Zoom and in the room?
Yes.
Yes, can hear you.
Perfect.
Yes, loud and clear.
I'm just going to share my screen. And yeah, I think the screen share came through.
Yes.
All right, so thanks again for inviting me and for all of the great organization so far. So yeah, today I led a keeping up with the theme of the workshop, I will be talking about some of the work we've been doing on 3D scene graphs, and maybe towards the end I'll show you like a quick sneak peek of what's to come in the next few months. But overall, it's just zooming back. I like to think of my research as teaching robots to understand the world around them. So imagine you have a robot in an environment like this, and robots given a wide variety of tasks, including ones that it's never been trained to do before, like helping someone find their keys, or like finding shoes that match an outfit, or so on. And to do like these tasks may seem very, very simple or trivial for humans, but these are extremely complex if you consider all the challenges that robots need to encounter through this entire process. So first step is, of course, knowing what is where in the environment, like creating some sort of representation, organizing the environment so that you can take these queries, ground them, and then figure out how to address these queries. Like once you know what is where, you can interpret the context in which the queries are provided, and then you can plan actions to achieve specific outcomes in the environment. And in general, we've been seeing this trend of like scaling, bigger models, more compute, more data, and it's resulted in this sort of unified transformer-like architectures or solution patterns trained on large data sets, which have shown a lot of progress. And in some ways, scale is essential, but it's probably not sufficient if you think of all of the applications where we've seen progress so far. And these very densely correlate with the scenarios where we have lots of training data, like we have billions or trillions of data points, like text, images, videos on the internet through which we can train these models. But when you start thinking of 3D content, for example, there's 4 or 5 orders of magnitude fewer data points for them, whatever data point might mean in the context of 3D content. And most of the data we have there is static. And this becomes more and more difficult as you go towards the real world. Like think of robotics, you have an order of magnitude fewer data points, including like robot control actions. So there's always this trade-off of you get closer and closer to the real world, it's more relevant to robotics. But the complexity also increases, while at the same time, like the amount of data you have to train these models also decreases. So in a lot of what I'll talk about, the solution pattern is that we leverage some sort of structure in the data or as part of the model that helps us learn faster from less data. And one such structure we'll talk about, keeping up with today's theme, is the notion of 3D scene graphs. And specifically, the take I will provide over the next 10 minutes or so is, like, we have all of these impressive vision, language, and whatnot, like models. Can we take all of the capabilities of these models and lift them to 3D for 3D perception and robot task planning? So there is historical context for scene graphs being used in robotics or in computer vision for representing the environment. So there's a lot of traditional SLAM or even, like, to an extent, structure for motion approaches that represent the environment as not just a bunch of points, but as a collection of meaningful objects, or like a bunch of categories, semantic segmentation attributed to each point in the scene. And more recently, like 2 years ago, we've been seeing very strong scene graph, like 3D scene graph proposals for these environments where you have multi-resolution representations. Like the highest level could be a building or like city block if you want to go like one step higher. And building comprises of rooms. Rooms comprise various places, and there's objects and agents, which is sort of agents as a complementary layer. But objects are organized into places, which are organized into rooms, which are organized into buildings, and so on. And before all of the recent advances in vision language models, a lot of these scene graphs and semantic SLAM or object-based SLAM approaches were close set, in a sense that all the classes you needed to know beforehand, like at train time, ideally. So all of the objects of interest are sort of this closed world. You only ever reason about them. And they also are largely unimodal. Like you take a class ID and that's the only thing you can address these objects by. And solutions tend to be very, very sensor specific. Like these scene graphs are constructed just off of specific like stereo or in some cases RGBD data. But if you now look at like, oops, okay, I think you can see this now. And since 2022, 2023, like last year and a half or so, we've been seeing this significant shift towards the open set setting, which is the assumption that you do not know all classes of interest at train time, but you do assume access to a very large train set that a lot of related concepts of classes are kind of covered in the train set. And we're also seeing approaches that are multimodal. You can have queries in the form of text or an image, and you are able to localize those specific semantic categories in the scene. So in this talk, I will focus on open vocabulary, 3D perception, and the specific angle is we will be using off-the-shelf models without any particular training or fine-tuning. So we will be open set, we will be multimodal, but we will also be training free. And the reason we want to be training free really stems from the fact that we get a new model or like multiple new models each day or each week. And we just want our performance of the overall system to scale as newer and better base models become available. So it's the setting where someone does all the expensive work of training a large model for you, and you are trying to figure out how to engineer using these models for 3D perception. And I'm going to talk about one of our recent works called concept graphs, where we build 3D scene graphs from data. And the key idea here is you have a sequence of input images, and you can run a number of open vocabulary detection segmentation algorithms to segment these. And often these segments are sort of over segmented, but if you run 3D mapping over time with semantic and geometric consistency criteria, you can organize these automatically into a bunch of meaningful objects. So what you see is on the top left, the original input scene, top right, segmentation, and you can often see how the cabinet is over segmented or the sofa is over segmented. And then over time, we just reorganize it into a consistent object. And quick way how we do this, we can also optionally use detections in the pipeline. You have post RGBD images, so we assume camera poses are available, which is sort of a crutch for now, but there are many ways you can get camera poses. Think of iPhone, you can use ARKit to obtain camera poses, and you get open vocabulary 3D masks or optionally detections as well. And you take all of these to build a 3D map. You fuse detections over time by associating semantic and geometric consistency criteria. But you also take these objects and run them through a captioner, an image captioner, to get captions for each of these objects. And you fuse those captions across views. And this gives you eventually a JSON-like text description that you can then pass along to a language model. And we've demonstrated its application in a lot of downstream cases. For example, over here, there's a ClearPath Jackal robot tasked with the query of finding something to wear for a space-themed party. I'm not sure how clear it is on your screen, but you can see that the robot, and the bottom right is the robot's view, it ends up with a t-shirt that says NASA written on it. Or in this case, there's a Spot Mini tasked with finding something healthy to eat, and there's mango that it goes to pick up. Of course, it's a plastic mango, and you can't really eat that mango, but that's what the something healthy to eat query resolves to. So, and again, here is like a full-size autonomous car driving itself to a shelter or white underpass to shelter from the rain. And another example here, video's a little lagging, but where you ask abstract queries like, get me something that goes well with Ronald McDonald outfit. The robot navigates these pair of red and white sneakers, saying, well, the Ronald McDonald outfit is red and yellow, and the red and white sneakers go really well with it. And you can also combine queries that mix text and visual context. So you can show this picture of Michael Jordan and ask something this person would play with, and it finds a basketball on a scene. So far so good. Like this is in some sense, it's a nice integration of 3D mapping with modern language models. So all we did was you take 3D scene reconstructions, you caption objects, and then you construct a scene graph out of it, and then you pass it along to a language model that acts as a task planner. And there's a number of extensions of this work, both from collaborators of ours and also from other researchers around. One particular aspect I will focus on for the next minute or two is this notion of incorporating more structure and performing more complex 3D understanding tasks using this kind of a framework. And the scene graphs are the core of all of this, where you can think of pipelines where you have these post RGB images, you can construct 3D scene graphs, and these are all open vocabulary. Like the nodes are open vocabulary objects. You do not have to see them prior to train time. The edges can also be a collection of relations that you arbitrarily specify. In our case, we use physical support or containment as the two relations of interest, but you could also imagine having just about anything else. And this is converted to a textual description, but in addition to this textual description, you have a library of, let's say, spatial, like compute distances is A bigger than B, compute volumes, get the K closest objects, or trajectory planning, a bunch of logical operators, and also a bunch of neural operators. So there's like a view synthesis operator, which is a Gaussian splat trained over the scene, which can synthesize novel views given a camera pose. Or there's describe around operator, which given a scene graph node and a distance radius, generates a description of all of the objects using language model, and an image QA agent, as we call it, which is under the hood another image language model that can answer questions about an image. And the idea here is, can we synthesize, instead of having neural nets directly output objects of interest, can we like synthesize programs by leveraging these modules so that we have more prescriptive 3D understanding? An example of that, for sake of time, I'll just run through one example. So one example is situated reasoning, where we basically say, if I were to walk from the table to the cabinet, would I pass by the ottoman? So this task, if you think about it, requires you to situate yourself in the scene and imagine you are walking from the table to the cabinet and then replaying the scene in your head of sorts, and then answering the question, would you pass by the ottoman? And then the way our approach answers this question is to do call it plan trajectory function, like plan in the trajectory from the table to the cabinet, and then call a view synthesis function to generate a bunch of intermediate views. And for each of these images, ask the question to an object QA agent, and then consolidate all of these responses to come up with a single response that, yes, you will encounter two ottomans during this trajectory. So this is an interplay of both these prescriptive symbolic operators and neural operators like the object QA, and organizing their outputs to form a coherent response. There's a bunch of other questions I will not get to at this point, but if we kind of look at how this fares with respect to a baseline that does not use any structure, or so if we do not use any structure, we struggle, like the scene graph significantly helps. And if we use the operators, it bumps up the performance even further. So with this, again, like I will just step back and leave you with some of these takeaways, like using open vocabulary, structured scene representations is a very promising approach for enabling new capabilities across like robot perception and planning. But the key here is retaining certain algorithmic and symbolic structure that allows performance to scale. You get new models each week, and you want performance of your overall system, like 3D perception and planner, to scale as these new models become more and more capable. So with this, I will take any questions if we have time, or yeah, I see that the coffee break is next otherwise.
Thank you very much for the great talk. Yeah, please.
Yeah, thank you. I just wanted to announce if there are any questions in the room, please raise your hand, and it would be great if you can come here and ask your question because we need a mic. But in the meantime, Azadeh and online folks, if there are any questions. Anyone in the room?
Maybe one small question from my side. How do you decide on the concepts? How do you choose them? Is there any way to automatically extract, like choose the best ones, or I guess you define them beforehand, right?
Good point. Like in the detector free variant, which is like just using open vocabulary segmentation, there is no premeditation. So we just get segments from something like FastSAM, which gives us like a bunch of masks from each image. And we just fuse these images using geometric and semantic consistency over time. Semantic consistency just means we compute like cliff features for each segment, and then we use that as an additional factor in computing our overall like data association score. And so in that case, there's really no premeditation. Like everything's decided by what SAM chooses to group as a single segment. And over time, if the clip similarity is high enough, they get grouped into a single object. It's not just semantic similarity, it's also like you also have to look at the fact that they're close enough, your spatial proximity holds too. But we also have other variants which are very useful for creating like task-specific pipelines for robots. Like if all you care about is reorganizing books, you probably want something that can detect books. So we have a way of injecting a prompt into the overall system. And but our code is already like open source. If people want to play with it, like you just say, these are the categories I'm interested in mapping. So you can effectively convert this to any number of closed set systems by just appropriately prompting it.
Thank you. Any questions in the audience there?
Not that I can see any hands raising. So thank you. I think this was a great talk, and let's thank our speaker again.
Thanks. Thanks for having me.
So I believe also that this is the break, right?
Yes, yeah, the poster session and break, and the posters will be presented in the ARC building.
Perfect.
And yeah, the numbers are on the website of the workshop.
Which is 60 to 60.
Yeah, 9.
Right. Great. And we are going to be back at 10:45, I believe, right?
Yes. Yeah.
Okay. Amazing. Thank you.
Thank you.
I'll stay online just in case, but we'll I mean my laptop is online.
Sure, I will share a slide for the poster session.
Okay, so maybe I can leave the laptop connected. Hey.
Or if you want, you can also disconnect it.
Okay. Yeah, the laptop is connected. So let's have it on.
Son, do you hear me?
How's it?
Yes, I can hear you.
I can hear you too.
Yes.
Yeah, I mean in the room.
Yeah, yeah, I can hear you, and everybody should be able to hear you too. I was just having problem finding the unmute button.
Oh, okay. So, okay, now we start the second part of the workshop. The first talk in the second oral session will also be online. I will start playing the video shortly, and the authors are available online for Q&A.
And the second author, I would appreciate it if you're here, just let me know. The second presenter in this oral session.
Hello everyone. Today we present our work, Ego-SG, learning 3D scene graphs from ego-centric RGBD sequences. In this paper, we focus on the task named 3D SGP, 3D scene graph prediction. The 3D SGP task is initially proposed by the below paper, where the network is trained to predict 3D scene graphs on localized objects. That is, given a class-agnostic instance segmentation of a 3D scene, the graph prediction network would try to infer a semantic scene graph from the point cloud. The instance segmentation of the 3D scene would be provided as a class-agnostic instance mask CAIM as the input to the network, and the network would to conduct prediction on objects and their in-between relationships. Most existing 3D SGP work expect to take the high-quality 3D reconstructed environment as input, such as point cloud, where their graph prediction network could be built upon. However, this assumption of high-quality reconstruction has limited its applicability in mobile or ego-centric applications, especially when accurate camera poses or SLAM techniques becomes unavailable or unreliable due to the hardware limitation and the power consumption in real-world use cases. To this end, unlike most existing 3D SGP approaches, we propose a new learning paradigm that learns the 3D scene graph from unposed ego-centric videos via a reconstruction-free manner. Our approach would take unposed RGB or RGBD sequences as input, focusing on the mobile or ego-centric applications. We first revisit the existing reconstruction-based 3D SGP approaches, as well as their potential shortage. Next, we present Ego-SG, our reconstruction-free solution for 3D SGP. To infer scene graphs from 3D environments, this approach highly relies on the reconstruction step, where the additional associated camera poses will be provided as input. Next, the perception stage, which includes the feature extraction and graph formulation steps. More specifically, point encoders such as PointNet and PointNet++ will be used to extract point-wise feature from the 3D environment. And the scan-level CAIM will be used to conduct point-to-instance feature formulation. Noticeably, the CAIM would only reveal the point-to-instance mapping information, but without releasing the specific object classification label. With CAIM, this approach completes the 3D object localization. The next popular module to be adopted for 3D SGP is the graph reasoning step. In graph reasoning, it has two functionality, the feature engineering and feature refinement. First, it would transform the node feature and use it to initialize the edge feature. Next, it would pass both the node feature and edge feature into a triplet GCN to conduct attentional reasoning. Eventually, the refined node feature and edge feature will be passed into 2MLP to perform the scene graph prediction for node classification and edge classification. However, their performance will be largely limited either when the SLAM techniques becomes unreliable or the ground truth camera poses becomes unavailable in the real-world use cases. To this end, we present Ego-SG, our reconstruction-free solution for 3D SGP. Ego-SG would learn 3D scene graphs from ego-centric sequences without any reliance on either the camera poses or the SLAM techniques. It would first perform the ego view perception on each frame for pointwise feature extraction and node feature formulation. Next, it would perform the graph reasoning on each frame for better feature refinement. Similarly, in Ego-SG, we also utilize CIM to perform the cross-frame node association for 3D object localization. Eventually, the graph reasoning module is also utilized at the global level to perform the video level graph prediction. Since the perception and reasoning process of the inferred graphs are performed on each ego view and the environment, we term these estimated graphs as the Ego-SG to differ them from the typical 3D scene graphs, which are learned directly from the reconstructed global 3D scenes. For the experimental setup, we first select the 3D SSG as our evaluation dataset, which consists of 20 class objects of NYU N2 format and 7 class relationships, such as attached to, built in, and supported by. For the evaluation matrix, we follow the 3D SSG to compute and report top N accuracies for object, predicate, and relationship predictions. For the evaluation of the relationship triplets, SRO, it measures the overall recognition of the subject S, object O, and their in-between predicate R by multiplying their scores jointly. Next, we release our experimental findings. The R3 denotes the system reliance on the 3D scene reconstruction. P, D, and N indicates whether the system take the ground truth camera poses, depth, or normal information as input or not. The first baseline to be compared with is the 3D SSG, which is also the first work proposed 3D SDP task. It would take the entire 3D scene reconstruction scan as input, and it would utilize the ground truth camera poses and depth informations. The next baseline is the scene graph fusion. Although it would take the sequence as input, it would still require the SLAM technique to perform the incremental scene reconstruction for the final scene graph prediction. During our preliminary study, we observed its high reliance on the ground truth poses, and its performance would largely drop when it's shifted into the estimated poses. Next, we present our reconstruction-free result, the Ego-SG with unposed RGBD frames. It's largely outperformed its counterparts with the compatible settings, especially when the camera poses become unavailable. We are also interested in further release the assumption of the ground truth depth information. So here, we utilize the medias to compute the depth estimation and list its result as a reference here. Here we present the qualitative result. For more visualization, please see our supplementary. We'd also like to further discuss over the different perception scheme. Unlike the existing reconstruction-based 3D SGP approach, our Ego-SG is compatible with both 2D and 3D pre-trained visual encoders, such as ResNet or PointNet++. Unlike the reconstruction-based approaches, our encoders could be flexibly switched when depth information become unavailable. One more interesting finding to share that all point-based entries outperform their competitors by a large margin, yet maintains much less numbers of trainable parameters. It validates that the depth information encodes vital 3D pairs for 3D scene graph recognition, and point encoders are capable of extracting them efficiently. To better understand the contribution of depth information towards the 3D SGB task, we further conduct the following experiments, where we find using estimated depth with point encoder seems a good option. Although it still falls short compared to the ground truth depth with point encoder, it would largely outperform the RGB alone with image encoder result. At the end, we present and identify 3 popular failure cases when utilizing depth estimation for 3D SGP. The first one is oversmoothing. The estimated depth might be insensitive to the object boundary. The second one is far position. The depth information at further positions might be easily omitted during its optimization. And the third one is illumination interferes. The scale of the estimated depth could be impacted by the illumination changes. With more advanced depth estimation method to be developed, Ego-SG-alike reconstruction-free framework could further broaden its application to build 3D scene graph from more conventional RGB videos, such as the large-scale Ego-centric RGB videos on YouTube. Thank you.
Thank you for the presentation. Chowi, can you unmute?
Yes.
Okay.
Hi.
Hi.
Nice to see you.
Nice to see you too. Thank you for the presentation. Are there any questions there in the audience? If not yet, I can maybe first start with the question. So your method relies on point clouds. What happens if the point clouds are too sparse? Have you tried with that? Or
For the sparse point cloud, I think we since we do the perception on the egocentric view, so basically we build up the partial point cloud for each frame, and the entire association is completed with the CIM mask. So basically, as long as the detailed information can be preserved as the current frame, we can be able to extract the node feature from the current frame, and we leave the following step to the eventual association stage.
Thank you. And maybe a follow-up question, since point clouds are kind of in a graph structure themselves can be represented as nodes. Did you try using a graph neural network directly for the whole process?
No, for the association one, in our supplementary, we try different like 2 exploration. So one of the one is like we try use a heuristic stage to like without any training process to add one node into the other, and we just try this kind of preliminary study for that. Yes.
Thank you. Any questions in the audience?
Perfect. Thank you. Any questions here in the room? No. So I think we can thank the speaker again and
Okay.
move on to the next presentation. The second presenter is in the room. And we have, yeah. Let's see. I think you have the PDF file, right, for the presentation? Let me see if I can share a screen and also. That is going to be a little bit challenging, given that it doesn't, when I do full screen, nobody can see that. So the solution would be to here. All right.
Okay, wonderful. Hi, good day, everyone. My name is Julian Novitz. I'm from the Machine Learning and Computer Vision Lab at University of Augsburg. And can we get this one? Yeah, that was side. Yeah, that's okay. Thanks a lot.
Yeah, sorry.
Yeah, no worries. Yeah, and we've published a paper, Review and Efficient Implementation, Scene Graph Generation Metrics. So before talking about what we actually did, I first want to define scene graphs for our paper, because as we've probably seen also in this workshop, scene graphs mean different things to people. So in our case, scene graph consists of relations and instances. And an instance is either a box or a segmentation mask, and it has an additional class layer, so human or blinder, floor, whatever. And the relations represent the interactions between those instances. So we've chosen the name instance because object is already taken for subject object in a relation. So we thought that instance might be a better suited name, at least for this presentation. Yes, so now that we've settled this, what our goal was for our publication was to make life as a scene graph generation researcher better and easier. And therefore we identified two problems that you have when you're researching a scene graph generation. And one thing is that if you, I don't know, at least when you're new to the field, you notice that we have all these nice metrics, recall, mean recall, and so on, but they're never really like precisely defined. Never. So it's just written in words, also good written, like, but for a really formal definition, that's often missing. And you have to delve like 3 layers into code and then maybe find this and be lucky. But we thought this maybe would be good to collect all those commonly used metrics that are used in scene graph generation, review them, combine them in one single space in the paper, and then formalize all these different steps that are required so that everyone can just read this section and understand immediately what this is all about. And the other thing is that when you're a researcher on scene graph generation and you want to write or evaluate the scene graph generation results, you have to use some way to evaluate them, right? And you can use some existing repos and try to surgically extract this code that is used to evaluate these models, or you use SGBench, which is a Python package that we've developed exactly for this use case, so that you have really nicely separated module that you can use to evaluate all the models without thinking to how do I integrate this in my code base? How do I get this running? So yeah, it's really, the idea was to make life easier for you as a researcher on this topic. So we've developed SGBench supports multiple metrics. Obviously, to extend them wouldn't be that much of a hassle. So if there's something missing, I think I see no problem why we shouldn't extend to that. So just talking about SGBench, the Python package a bit. So what we do is we have
Sorry
these
to interrupt you, but on the Zoom, we only see the first page if you have changed the slide.
Okay.
Interesting.
Oh,
Okay.
screen sharing was paused.
Now we see.
I don't know why the screen sharing was paused, so.
Okay. Yeah, now we see the correct.
Okay, sorry.
Yeah, no, of course. Okay, if I now change slides, you see it?
Yes, yeah.
Okay, wonderful. Yeah, I think, yeah, this is what was the slide before, but I think I've also told everything. So let's go to the next slide. The Python package tool. So what SGBench does is we have the output relations and the output instances, and we have the ground truth relations of the ground truth instances. The first step is to match ground truth instances and output instances. because you have to like, is the predicted human also the ground truth human, and so on. And you have this mapping, you can map the output relations to use the same reference point as the ground truth relations, and you just have to compare the predicates, right? So the more difficult or more computationally more challenging part is to match these instances onto each other, and then just counting how many relations have been recovered. That's the easy part. So that's why we first do this matching process, and then with these matched instances, we can easily calculate all these relations. Right, so what you can do is you can just pip install and then sgbench, and then use these 3 lines of code there to evaluate your model. Just as a warning, so these lines are for a new version, which hasn't been updated yet, but I guess you can expect it in the coming week or week after. You can also use it as a CLI tool. Just put in the annotation file, ground truth file, and your model output file. One comes with us in the next slide, and then you can get some results back on the metrics. So about the model output file, it's also something that we wanted to improve for researchers and scene graph generation. So you can have these pickle files that tend to be really huge. You can only be read by your code base because they're maybe using some class references, and so you need some code for that. So we thought it would be really nice to have a file format that anyone can read, anyone can write, and it should be fast, small, and efficient. So we thought for, at least for panoptic scene graph generation, you need segmentation masks. And that's why we need some image files. So I think the most commonly used way is to just store NumPy arrays as pickle files. But that's obviously really resource inefficient. And another way would be to use TIFF files, for example. So why did we choose TIFF files instead of PNG files, for example? It supports arbitrary number of layers. So you can have overlapping segmentation masks. So for example, you have 100 instances in an image, and you want them to partially overlap. You cannot really do this in PNG, because then you have just 3 channels. So we chose TIFF to have 1,000 layers. Supports compression, which solves the file resource requirements, and it can be read by, I mean, virtually anything that supports like these files, or any program language you want to use supports, I think, TIFF files. It's really high chance that you can read those. And right, if you're not doing panoptic scene graph generation, you obviously don't need those TIFF files, but if you do, then yep. And to store the relation files, we decided to use JSON as the file format, just to have a format that anyone can read, anyone can write. We thought about using HD5 for SQLite, but for HD5, you would need an additional library, which we tried to really try to keep the dependencies to a minimum so that it really works with your code base. And SQLite would also be maybe nice, but I think JSON files are just easier to work with. If you can human readable, you can edit them. It's built in everywhere. Yeah, that's why we decided to use JSON annotations. So if you look at this, you see that this file format that we devised for sgbench can be read and written even without sgbench. So you're not locked into our solution here. You can have, I don't know, C++ implementation where you want to evaluate these files. No worries, no problem. You're not locked into some Python class representation or some binary format where you depend on our implementation. Yeah, and the good thing is that we can, using this file format compared to these traditional pickle files, we require much less space and on the disk, because we don't store all these images as bitmaps, and we also only store the information that's required to evaluate these models. So we can still generate the same scores, the evaluation scores with these files, but while reducing the number by quite a lot. So, and the last thing that we've built is it's an evaluation server. where you can upload these files and they evaluate the scores for you. So if you have this, then so with this web service, you can guarantee that everyone uses the same evaluation code, which I think is quite beneficial if you want to prove that you haven't tried to trick someone with your evaluation method, for example. So anyone can register, takes a couple of days, and then it's unlocked. And also, if you upload something there, you can add links to your project page for publicity or whatever. And we'll also open source the web service code. Yes, so we hope that these changes will improve your life as a scene graph generation researcher. And I'm open to questions. Thank you.
Thank you for the presentation. Maybe I can start with one question. So does your benchmark only support the semantic scene graphs, or if the scene graph is also in a different setting, for example, if it doesn't have, it has undirected relationships or only 0 and 1 binary relationships, would it support it or not?
Probably.
Yeah, so we're
trying.
Okay, we're trying the microphone at the moment.
Play with this. I think the is fine. It's just itself. You can probably answer because you didn't.
Okay. Yeah.
Just speak up.
Yeah. Okay, I'll try. So the question was if it only supports semantic segmentation, and that's it. And we can, well, obviously we're limited to some applications here, also some problem formulations, but there is no problem in extending this to, I don't know, binary relations or uniform, unidirectional relations. So at the moment, it supports box scene graph generation and semantic scene graph generation. But I see no problem at extending this to other fields. Also, I think it would be quite trivial to do so.
Thank you. Any other questions there or on Zoom?
Any other questions in the room? I think we do have a couple of minutes, and I actually had a very quick question. So you talked about a number of metrics. That's a great resource, I think, putting all of them together. But have you thought about scene graphs that are applied to video and understanding? Like, for example, action graphs that are repeated nodes, but the relationships change over time. Does it change how you define the metrics?
So these are developed for 2D scene graph generation. So that was the main goal. So everything that you can use for, so you could calculate those per frame, I guess, using the library. I don't see any problem in that. However, if you want to extend this to video, then you of course have to, some of these concepts don't apply, I would say. So it's not built in at least, yeah.
Okay, great, thank you. Let's thank the speaker again. It's been great, and I believe our next speaker, yes, we have Professor Trapp online. So let me see if I can.
Hi. Can I share
Hi.
screen or how should we do it?
I will do a short introduction, then you can share screen.
Okay, perfect.
So, yeah, our next speaker is Professor Volker Tresp. He is a professor at Ludwig Maximilian University of Munich and also with the Munich Center for Machine Learning. His team has been pioneering in machine learning with knowledge graphs, temporal knowledge graphs, and scene graph analysis. And he's also a co-director of the ELIS program, Semantic, Symbolic, and Interpretable Machine Learning. And we are glad to have him today to give a talk. So I stop sharing and we can continue.
Okay, can you see my screen?
Yes, but it's not in presentation mode.
Yeah, how about now?
Yeah.
Okay,
Yes.
great. Perfect. Yeah, thanks a lot for inviting me. I hope you can hear me well. And thanks to the organizers. And I'm sorry that I cannot be in Seattle. Probably a very nice place and conference. So my co-authors here are Hang Li, Zahan Sharifzadeh, who is now with DeepMind in London, Dario Konopatsky, now with ETH, and Hyun-Poo Ma. So we thought about, so I like this proverb from Goethe, you only see what you know. So Goethe looks at this scenery and he sees maybe some mountain range, and then he recognizes that this is Munich, and then he knows from his semantic memory that Munich is capital of Bavaria, and maybe he has some nice episodic memories about visiting Munich. So this completely enriches his vision experience, and also really make him understand what he's looking at. So we wanted to look at the question of also from a cognitive biological viewpoint. So how are they connected? How do they interact? How are semantic and episodic engrams implemented? So these are memory traces in the brain. How do they interact? How does perception and memory interact? And why are they sub-symbolic but also symbolic? Now we have some maybe visual impression of a past memory, but we can also immediately talk about them. And a short out exploration in direction of reasoning and language. So this is like a small part of some introduction to our larger work on the tensor brain. So this is a very simple model. So an n-gram consists of an index, and it can be like one neuron or a small set of neurons. And this index I here, this is for Sparky, is connected to the representation layer, also called global workspace. And the connection weights here are the embedding of that index, in this case of Sparky. And these directions are bidirectional. So if we activate this index, it will form the embedding on the representation layer. And if the representation layer is excited, it will maybe activate this index. And so an n-gram always consists of an index and the embedding vector. And if the index is a concept, like an entity, a class, or attribute, it's a semantic memory. And if it's a time instance, it's an episodic memory. So how does this work in practice? So we have these two layers, and so to recall an episodic memory, we activate the past time index here in the index layer, and this index then activates the representation layer with the embedding of this memory. And this also goes back to earlier processing layers in the brain, which we call embodiment. So we always have embedding and embodiment. This information is then propagated in time, and so now we can immediately. So this gives us some visual impression maybe of this past memory, so of this past episode. But then we already starting the decoding. So we recall there was Sparky in the image. By decoding this embedding vector, Sparky then is activated and reactivates the representation layer. So the brain knows that Sparky, this is now about Sparky, and then the object is detected, maybe Jack, and then the predicate looks at. Now, so we have this classical triple structure of knowledge graphs, and everything is fed back to the embedding layer and then also to the embodiment. So this is how our idea of how episodic memory, and this is repeated many times. So for the same AT, for the same memory, we can detect or decode many triples. So in together with this sub-symbolic impression of this memory, we also have the triple expression of what was going on. And semantic memory is very similar, only that we start by activating the subject. For example, in this case, Sparky. We also have an embedding for Sparky, and then some understanding of what Sparky looks like, what he acts like in this embodiment process. Then maybe Jack is activated and then owned by. So we know that Sparky is owned by Jack, respectively. The brain knows that. And perception works with the same machinery, just in another operational mode. So the input comes from the vision, activates the representation layer, and that then decodes in the image the subject, the object, and the predicate. Again, maybe finding in the image that Sparky looked at Jack. And so here it's mostly a bottom-up operation and not so much top-down operation. But everything works with the same machinery. And if we don't need the predicate, for example, if Sparky and Black is activated, then it means that Sparky is black, so we don't need the predicate. So we have sort of a little bit of a shortcut here, which also leads to generalization. So in this, in a layer representation, so this was unfolded in time. Let's say we have bounding box content from the bottom up, and then a deep convolutional neural network, which activates the representation layer, and this then activates the index layer, and this goes forth and back, and the connection weights are the embeddings of the corresponding indices. And this whole processing is also supported by another layer, the dynamic context layer, which provides a nonlinearity and some nonlinear mapping. And so the ideas or what we propose is the brain doesn't really know what is true and false. It only knows what is brought to the attention of the representation layer by the internal observations, by this generative sampling process. And in the episodic memory, we can decompose, as we discussed before, we can sample an S given the T, an O given the S and the T, and a P given the S and the O and T. And we repeat this sampling many times to decode or recall an episodic memory. And we argue in the paper that this is proportional to our confidence that this statement is actually true. And we have a similar relationship between with respect to semantic memory, only that here we are starting with the S, the subject we want to have information about, then the object, and then the predicate. And also here we can argue that this is proportional to our belief that this triple is actually true. But the inner language is this sort of this sampling language in the brain. And we can also look at this as a generative recurrent neural network here on the right side with the representation layer, the green one, which unfolds in time, and then the input from the image bounding boxes. And then, so the only difference is how we deal with the output. So we are predicting the output, we are sampling the output, and this information which sample was generated is fed back to the representation layer. So that's the main difference to a recurrent neural network, which we are proposing here. Because the brain should know what we are thinking about. It should not just say, I'm happy that you decided that we detected Sparky in the image. The whole brain needs to know about this. So it needs to feed back into the embedding layer and then also in the embodiment. We also have some theoretical reasoning why this this addition of this sampling, which is we are proposing, they're not some complex interaction, but the different sources can produce samples like perception, but also episodic memory, semantic memory, and we formalize it in this Dirichlet fusion model, where we combine observed data with semantic memory, which is essentially something like a prior. In particular, we propose that a perception generates samples from the perceptual posterior, so the probability of the triples given the perceptual input, recent episodic memory from the past posterior, so these are both posteriors, and the semantic memory is something like the prior. So what is our default knowledge about things? But we don't combine it in terms of prior and likelihoods. It's prior and posterior, what we are proposing here. So here's an example about semantic memory, which is about things we know. So we know that lines are dangerous. We don't have to have a personal experience. And here we have two bounding boxes in this image. One is identified as Sparky, the other one as a bench. Or more concretely, we have several labels for this bounding box. It's Sparky, but also dog, mammal, living being, young, white. And for this second bounding box, it's a bench furniture, non-living being, old, and other color. And for the triples, we have dog sits on bench, living being sits on furniture, mammal sits on old, white sits on bench. So it's sort of this back of decoding sort of idea. And from the semantic background, we add that Sparky is owned by Jack and Sparky is loved by Mary. So this sort of this triple background is brought to the attention to the brain when this, in this case, Sparky is detected in the image. And we can generalize statements because a subject can also be a class or an attribute. And then we can, because maybe the dog in the image is unknown to us, then we can just know that it's a dog. But also since the subject can not just be an entity, but also a class, we know, for example, the dog is a mammal, is a living being. They're often young. Dogs are often on grass. They're often behind a person. Or here the person often wear shirts or wear glasses. So we can also add this default knowledge or background knowledge about concepts. Now here a mammal can be a dog with 40%. Mammals are often on the street in the data set, and even we can talk about a description of the color black. So with 25%, it's a human being. Or something is on a person, maybe a hat or something. So so we can also model this sort of more general background knowledge, not just instance oriented. The scene graphs are typically concept oriented, whereas the knowledge graphs are typically instance oriented. And we did a cluster analysis or TSNE analysis of the embeddings, and we found that they're quite meaningful. In particular, I mean, all these things are nicely clustered, so trucks, planes, jackets, buildings, and so on. And also the embedding of the concept truck is very close to the center of the cluster of the trucks, which we did not enforce. No? So, but it means the sort of the algorithm or the model understood what is similar, that like a concept tree should be close to the instances of tree. And we thought that that's a quite nice result. Then episodic memory is about things we remember. So and we distinguish between recent episodic memory. So that tells you why you are where you are, why you are in this room listening to this talk. So here, for example, this poor mouse, if the mouse forgets that it's in this cup because the cat was chasing it, it will not live very long. So recent episodic memory gives you orientation about recent events, and so you don't need a complex state vector to do that. You just have to recall recent events to know why you are where you are. And remote episodic memory is more about decision support. That if you have a bad experience with a line, you don't have to, you don't want to repeat that experience. So it gives you a decision support and guidance in acting. And we also propose that episodic memory can also be active or a nice concept for the future. For example, if you read in the newspaper this evening, so you don't have to have a big predictive system, there's a football game and it will rain, then you expect bad driving conditions. So this concept of having episodes in the future might also be quite interesting. And also our embedding for the time index is meaningful. We don't see this amazing clustering, but we see, for example, here we have party sceneries, here we have sports sceneries. So also here, semantically, this organization of the embedding vectors might make sense. We also looked a little bit at reasoning. So embedded reasoning essentially is reasoning by adapting the embedding vectors. And if we know that Sparky is a dog, then we get the embedding vector maybe close to dog for Sparky, and that can add additional knowledge. And when we refine our information about Sparky, we will also refine the embedding vectors. We also would make a clear statement what symbolic reasoning is. So symbolic reasoning would be reasoning which only uses the indices without the embeddings. So if Sparky is a dog, then we can infer that Sparky is a mammal, and we don't need any embedding vectors for that. Currently, we don't have a model for that, but I think it's nice to have a clear separation of this embedding-based reasoning and symbolic reasoning. Then we also have symbolic embedded reasoning, which essentially means when we say that if Sparky triggers dog, then dog triggers mammal, and the brain can conclude that Sparky is a mammal. No? So we have these two triples which trigger each other, and we get a little bit of this subclass generalization. We propose that this is, I mean, this triple language we have been describing. First of all, it's also going on in animals, but it's also like something like an inner language, like a nervous inner language, which is cleaned up in some adaptation process, of course. But that natural language, of course, is much more sophisticated. It's more about justification of what we did, arguing that what we are planning to do is the right thing. So it's not the same thing, but we would think that the outer language is sort of based on the inner language to some extent. This is how it might look in the brain. So we have people found these indices, so these famous Jennifer Anderson neurons in the temporal cortex. And so ideally it would mean, or some interpretation, that there's a single neuron or maybe a small set of neurons which are responsible for representing this person. Of course, there has been a lot of discussion on this result, and then we have these results from Hood from Berkeley, which sort of maps surface of the brain to different semantic concepts. So that would be what we would probably interpret as the representation layer or the global workspace. And also interestingly, Dehaene argues that the brain is a slow sampler. Now you might have noticed that we always have the serial sampling process going on, which slows down things. But language is a serial thing, so maybe it's not so strange for language for the brain to have also a serial bottleneck somewhere. So in conclusion, I think time is running up. So we showed that perception and memory can be formulated in one model, essentially in different operational modes of one model. So they rely on the same brainwave as we're proposing. And there's always an interaction between subsymbolic and symbolic recognition. So there's no symbolic recognition without some sort of embedding or embodiment, and also and vice versa. If you have an embodiment, it's automatically embedding. It's almost always decoded into triples, into indices, into symbolic representation. But finally, maybe the statement. So we would propose that this is quite a plausible mechanism for some of the brain functions, but the brain does many different things simultaneously, and maybe the same thing even in different ways. It addresses a particular problem with several strategies, and we would propose that maybe the model we are proposing is one way how it solves some problems. Of course, vision is much more complex, has many more aspects, but maybe other modules are more important for those functions, and everything is then sort of integrated in some form of awareness. And so, yeah, we are quite proud that this was published last year in Neural Computation. So if you want to read up on it, here's the reference. So thank you very much for your attention.
Thank you very much, Volker, for the great talk. Are there questions in the audience there?
Anybody has any questions? I don't see any hands yet from here.
Maybe I can start with a question. So there are some data sets recently, like Ego-40, that are egocentric. Do you think it would be interesting for those data sets if in those cases the subject would be the person looking at the object, then would it simplify the Bayesian and like
yeah, of course, that would be very interesting. I mean, essentially, it is egocentric what we are describing, only that we had to work with the data we had at that time, because perception, of course, is a very personal thing, and it involves the experience of the agent, and the prior, of course, maybe can be changed or adapted in different ways. Of course, if you, for example, if you have a we have some form of perception and also sequential perception. But if this is very rich, of course, you can combine the different recognition processes. as in any video processing. So so that would help a lot, and then also would refine the prior. But we always make the distinction. So our prior is the semantic memory, and that changes slowly. That's not going to adapt very quickly. So if you want to remember something, and maybe somebody was not married, and then in your semantic memory, this person is still not married, but then maybe he married last week, and then you have the memory of this episodic memory. So this prior changes slowly, but the perceptual prior, which might bias your perception in some direction, that can be a different mechanism, and it would interact with the perceptual processing and not so much with the memory. So we think the memory is a slowly changing thing. And if something contradicts your semantic memory, you would remember the episode, which tells you that, oh yeah, no, it's not true anymore. Something has changed. No.
Thank you. Any other questions on Zoom or in the audience?
I'm gonna wait 7 awkward seconds. Okay, we waited. Thank you again for the speaker.
Thank you very much.
Thank you for your attention.
Okay, I will quickly share my screen. Our next speaker is Dr. Brian Perozzi. He's already there in person. He's a research scientist on the graph mining team at Google. He works in the areas of data mining and knowledge discovery, machine learning, network science, and natural language processing. Brian's research at Stony Brook focused on applying representation learning to applications in social network analysis and natural language processing. And his talk today will be about giving a voice to your graph. Thank you for joining us in person.
Thanks for the introduction, Azad. So we should probably maybe mute that, and then I'll unmute myself. Yes. Sorry, this is really hard to do on the screen. Okay. Yeah, so thank you so much for the introduction, Azad. And I'm going to talk to you about something today that has almost nothing to do with scene graphs. And I don't leave, because I think it will still be cool. And the application, it's about more general than like kind of beyond scene graphs, right? So I'm not going to talk as much about the visual element, but instead, like, how can we best represent structured data of any form for large language models? And generative AI models in general, right? Which all kind of have this discrete interface. So I'm part of the head of the graph neural network team at Google Research. We kind of have like a dual mandate of applying graph structured models around the company. And so we do a lot of that. We also do a lot of research in the area, and then we kind of build infrastructure to hopefully make applying the models easier. Is that good?
Notified the workshop organizer.
I can just talk loudly.
Yeah, that's great.
All right, I'm just going to talk even more loudly. So the motivation here, right? So we have this powerful new tool, generative AI models. They allow us awesome new capabilities in many different modalities like language, vision, and video. But there's weaknesses that are stopping us from applying them everywhere. You guys have probably heard about this a lot. There's the hallucination problem, right? A model will confidently say something that's incorrect. We go beyond that. We go to the freshness problem, right? So if you train the model, these models are expensive. They take a long time to train and a lot of resources. And then they're stale. Like the instant you stop training them, they don't have new information, right? So there's a freshness problem. And then there's also kind of a privacy problem where you can't train the model on data that you don't want it to tell everyone, right? So if you have some special data about yourself and you don't want the model to just kind of regurgitate that to everyone, you've got to somehow not train the model on that data, but have it available for it. And getting back to it, there's also this problem of cost, right? Like they're expensive to train, it's expensive to do inference. So like anything we can do to make these models more efficient is desirable. And so how can graphs help? So graphs can help kind of in two ways. So a lot of the problems that I talked about with the kind of the freshness and the privacy and like trying to put more complex data in the prompt. This is where like graphs are used to represent knowledge. It could be the knowledge of how things are related to each other. It could be the knowledge of what's going on in the scene of a video, right? But like graphs are this nice kind of human interpretable way to structure the knowledge, represent it, and reason about it. And if we can use graphs to represent this knowledge that we know to be true, and we can get this into the context of the large language model, or somewhere else in the large language model better, we hope we can improve a lot of these, like helping the model have access to the right data at the right time. The other thing is that graphs allow us to decompose the data. So the hierarchy and the structure of the graph itself allows us to maybe do clustering and work with it at a coarser level of the data than we would otherwise be able to. And so this is another advantage for graph models. So graph models versus transformers, graph models they're more parameter efficient. A graph model can do more with less, and they also they have a higher sample efficiency. So with a couple examples and a good graph, you can learn something. But if you want to transform it to learn that, you're going to need a lot more data. And so there's four ideas that I want to talk to you about quickly today, and I don't have a lot of time to talk about any of them, unfortunately. But if you have other questions, please follow up. The first idea is graphs as text, right? Can we encode graphs, like graph structure data, in text in a way that makes it easy for models to use it? And then the second idea, which is kind of related, but like graphs as embedding. So if we don't want to encode the graph as text, we think there's a better representation out there. How can we learn a better representation of the graph for the model? And then we'll get to the next two after talking about the first two. So yeah, question one, how to best encode graphs as text. And this is this work, Talk Like a Graph at ICLR. We're really interested in text because it's the dominant interface for large language models. This is kind of like a new capability to be able to talk to the machine and get an answer back. And so a lot of people are using it this way. And so in this work, we explore graph prompting and graph encoding and the analysis of the effect of the structure of the graph on how well the model can do. It's kind of funny because the model is very simple. So we're just going to take text and put it into Gen AI. Right? So it's a paper at ICLR that has no learning and no representations. I don't blame them, not me. So the framework itself, we're going to vary this graph encoder function and the prompt question, the way we're trying to get information out of the model. And what does that really look like? Well, the prompt is now going to be some verbalization of the graph. And then there's going to be some verbalization of the connectivity information. And at the bottom, there's going to be some sort of like question to see whether the model really understood what we were talking about. And it's going to be a graph-centric question. So we'll ask it about the degrees of the node or whether things are connected, stuff like that. That's all going to go into a frozen model. So a lot of what we do is working with frozen models. Then we're going to get the answer out. And so, we'd like to find the best encoder and prompt question to, help the model answer these tasks. And to kind of bring it home, this is my favorite example, I think, from the work. But like, what's in a node ID, right? So we have a picture of a graph here. We have a lot of different ways that we could describe it to one another. But what if we used fantasy characters? Just something totally weird, right? Okay, so this yellow node, this is Daenerys, right? For my Game of Thrones people. Bran, yeah, okay, so that's Bran. Maybe that one's Ned. So we can give every node sort of like a domain name about from some fantasy story, and we can write like a little verbalization of it that says like, oh, here's a friendship graph, and these characters are friends with each other, blah blah blah. How would that affect performance? Kind of crazily, that was the second best zero-shot encoder, the Game of Thrones encoder, right? Like over many other different choices. Now, the other one, maybe interestingly, is like using politician names was the best encoder on this particular model. And so like you can think when you're telling a model a story about like political relationships and who's related to each other, like that might put it in the right headspace to think more relationally about it. Now that's as we change the prompting type, as we change the information that we give the model and we give it more, it turns out that that's different kinds of prompting. So we varied all these different kinds of prompting. Using the the storybook version of it doesn't work as well as the abstract version when the model has more context. Lower is better here. This is like the ranking, average ranking, basically, across all the tasks. So an abstract representation works when we give it context. But if you don't have as much context, the model was actually doing better with like telling it kind of like a story with tokens that had more refined representations. And you know, to show you like, I guess, you know, you might see these results and say like, hey, why do I care about this at all? There's no way this could work. Okay, so we've kind of been doing a leaderboard over the last year or two for these kind of metrics. And in the beginning, I think I agree with you. Like, so this is accuracy numbers. So like 100 means that the algorithm, you know, it's working like as well as an algorithm could, always finding the answer. If it's low, you know, then okay, it's doing like a really bad job. So, you know, we're doing a bad job on things like counting edges is really low, and some of these tasks we hadn't measured in, you know, September. But if we look at what models are doing nowadays, like, so this is like from a month ago with, you know, larger and more capable models. In general, you see like there's a lot of these bars that are, you know, they're not all at 100, but they're getting a lot higher, right? And across that, the big models like GPT-4, the big Claude model, Claude Opus, and Gemini are all doing, you know, really well on these tasks, and they're kind of getting better. So every time we go out and we measure, we see that models are getting better at doing graph-centric tasks on these synthetic generated data. So, you know, there could be a future where we can encode graphs as text and the models will solve everything. Who knows? Maybe. There's another question though, like if we don't want to do text, can we do better? And so in the next line of work, what we did is look at learning an encoder. So it's kind of the same model as before, but instead we're going to learn this thing called a graph token. It's going to use a graph neural network to encode the graph into a sequence of tokens. So the verbalization of the graph is going to be these generated tokens that go next to the prompt. And then these are going to go into a frozen model. So the model itself is not adjusted, but we do learn the encoder from the model's gradients. So it's like a variant of parameter efficient fine tuning. And just to quickly show you what these kind of results look like. So using an older model that we did some of our early analysis on. So okay, that's POM 62 billion. And then we can take a model and learn something that's better than it. But if we take the same tiny model and add graph token to it, it outperforms the large version of the model. So the large version of the model has substantially more parameters. Unfortunately, I can't tell you exactly how many, but you're going to have to believe me that the small version of the model and the large version of the model are kind of wildly different. So just by attaching a little graph neural network with like 1 million parameters to it, we're able to boost the capability, the graph capability, way beyond what the LM can do by itself. So learning the encoder, like the graph verbalization, can work a lot better than the text-based prompting that I showed you, and can make small models very competitive. And you know, because I don't have a lot of time, basically every one of these results has a paper with a lot of extra information in it. So this is kind of like the TLDR version. But what else is at the intersection of graphs and large language models? There's two other ideas that we found really exciting lately. One idea is on the basically theory result on the graph capabilities of transformer models. So where are GNNs the right thing to use? And where are transformers, like either just like a raw transformer or like a large language model, trained transformer, where are they the right thing to use? And then the other idea is how can we use graphs to actually generate data for evaluation and training of transformers to make them better at tasks. And so this is the intuition here is that maybe I'll get to that in the next slide because there's 1 or 2 slides on it. Okay, so when we were looking at what we could do with graph algorithms and transformers, we wanted to try to understand when was the right time and place to use each of these methods, because that's kind of that's what we do. So we're looking when we look at the transformer results kind of on the next slide here, we're going to be looking at the text of like the token only representation of a graph. And so there's no text, but there's a discrete token for every vertex and a discrete token, like pair of tokens for every edge. And then there's like a task token at the end. And this comes from the token GT representation. So we took the graph like QA tasks that I talked about in the talk like a graph section before. And then we tried to figure out how much, like how big, like wide and deep a transformer model had to be to solve that, that perfectly. And so we came up with this complexity hierarchy of graph algorithms on transformers, which are kind of based on, are they looking at the global view of it, or are they doing like a local search? Those are kind of the two kind of large paradigms. And the experimental results, well, I mean, I think they show things that are known, but maybe I hadn't seen them, people say them in exactly this way. So right, obviously transformers excel at global tasks, right? They can kind of learn the connection between any pair of nodes. And so on connection or on tasks like shortest path and connectivity, you know, we see the transformers doing well. And then like we see that, you know, pure GNNs have capacity tasks. So when we take those tasks from before and we train them on 1,000 samples, you know, we can see that the GNNs are doing well. So like the MPNN model is like perfectly solving node degree, perfectly solving cycle check, basically. On global tasks, we see that, you know, there's less of a gap with 1,000 examples. So the bias of the MPNN is still making it better on shortest path. But you know, with more data, transformers can become competitive. So if I just go to the next kind of columns where we're looking at 100,000 training examples, we see that, okay, on the local tasks, the GNNs are still winning, but the transformers got a lot better. And the transformer on the global task can just like wildly exceed what the GNN is able to do. And so, you know, it kind of hints towards the regimes where we want to use GNNs, which is like ones that are doing like local tasks where we don't need, you know, and we trust the graph structure a lot to help solve it. But if we want to do something larger or more global, we would want to use the transformer. And so I just want to note that these, you know, the transformer model here is 60 million parameters, and the GNNs are much tinier, so they're 100,000. And so finally, and maybe my last minute, this idea of using graphs to help with synthetic data generation. So synthetic data, you know, transformers have basically trained on all the data that we have available, you know, movies, videos, text, right? They're like, these things are data hungry, and we've kind of run out of data. So we're looking for new means of getting data. So synthetic data, it offers a couple advantages. One, it's harder to memorize. And so this is good if you want to evaluate them, because you know, you're trying to basically see how much has the transformer stored in its parametric knowledge versus how much does it really understand like how to reason or like how to do a more abstract task. And you know, we hope the graphs can help here. So we have kind of, you know, the way that people were evaluating temporal reasoning was basically like giving kind of like a sequence of real world examples and then asking the model about it. But the model already has been trained on a lot of real temporal examples. So when we go to like an abstract version of it, where the entity names are masked and the type of the relation is masked, we can kind of get a better understanding of what the model is really able to do. Now, how can graphs help here? Well, we're using graphs to come up with all sorts of weird temporal dependencies. So like it's kind of like making random knowledge graphs. So we can generate graphs, we can assign entities and relations to the names and edges, and then that gives us kind of like a knowledge graph or like a relational database. And then from that, we can kind of look to find like a question in it, like, oh, okay, if there's these two abstract entities and they have like a time period like this, like how do you know, what was the gap, or what, you know, who was doing something else at the same time. So we're generating these kind of random questions. And just to show you what like different graph generators actually are creating like different databases that they look like, so we can, using all kinds of random graph generators, get all sorts of weird structure that people weren't evaluating on. There's a lot of results in this paper too, but I don't have time to go into them. So the conclusions here are adding graph information can help frozen LLMs solve graph tasks. The way that you represent your structured data does matter a lot. And you know, while transformers are less sample efficient than GNNs, with enough training data, they do get a lot better. So I think that's kind of like the takeaways. All the papers I talked about are right here. If you have any other questions, I'd be happy to answer them now or after the workshop.
Thank you very much for the very interesting talk. Are there any questions on Zoom or in the audience?
Any questions? Oh, yes.
Yeah, I guess maybe I missed this detail, but how large are the graphs that you're working with, and how does performance kind of scale with the size of the graph?
All right, great question. The question was, how does performance scale with the size of the graphs, and how large were they? So in order to okay, so this is, I get this question a lot. We were evaluating older language models that had smaller contexts, and we wanted to be able to store a complete graph in them. So those were the initial limitations. That led us to generate graphs with 20 nodes and up to 400 edges. There's no reason we can't do more than that now with larger models that have much bigger context windows, but we were evaluating kind of like the 2 generations ago of like large language models when we started. In general, though, as the I didn't have the slide in this present, but as the models have, like there's more in the context window, they do worse. So you'll see this degradation, and this is like a fairly standard result, like the more kind of unrelated information in the context, the harder it is for the model. And it's the same with the graph algorithm. So as we add more edges, generally performance goes down. And you know, I would expect that to go with more nodes as well, but we have better readings on like edges right now.
When you have the versions which aren't the text at the same type, you know, being encoded, how general is that over a particular class of graphs, of a particular type of data?
Yeah, great question. So the question is, when you're using like a graph token learned encoder, how general is it? So both in the paper and in some backup slides, I have some analysis of the generalization. We found that when you train an encoder on one task, it can generalize, like both the embedding itself. So like we'll train an encoder on like using one task, and then create an embedding for like, you know, a bunch of graphs and then test it on another one. And we do actually see a lot more generalization than I expected there. So it's not like they just have one task, but if you train something for connectedness, then it can do something with like bipartiteness and something with like shortest path. Like in some cases, the generalization isn't super high, but I think that, you know, there would be ways to even make it generalize better. So we didn't try to get it to generalize at all, and we saw, you know, some generalization. And you know, I think that there's a lot of headroom there that could be explored further.
Maybe one follow-up question here. So, do you hear me?
Yes, maybe.
Okay, so I was wondering how would these embeddings handle domain shift, for example, in case of medical knowledge graph or medical graphs, if you train on normal text and then want to... Do you hear me? Or...
Sorry, can you repeat that question?
I was wondering how would the graph embeddings handle domain shift? For example, if we want to train on normal text and then then fine tune or test them on medical knowledge graph or medical text in general.
Yeah, I think that's a really good question. So we did
Could you repeat it
yeah.
to the audience, because...
So yeah, sorry, to repeat the question, how does this kind of representation handle domain shift? And between different applications, like if you trained it on biomedical, could you reuse it on something else like citation networks? Well, we've done like an initial evaluation here, and we found that first, interestingly, the type of the relations, at least in the text form, the types of the relations didn't matter as much as you think. So we would ask the same kind of question twice and kind of vary the type of relations and then see like what the diff was in the performance. And the model could kind of still answer it. So we could do it with like a regular graph or change it to be a heterogeneous graph with like different kinds of edges, and the model would get about the same performance. So that's one result in the Talk Like a Graph paper. When we learn the encoders, we kind of have a choice, because if we make the learned GNN encoder more like a more heterogeneous network, then it will be less able to transfer for sure, because like the GNN encoder is going to have to get around those relation types. But it seems like the large language models aren't as like specific or peculiar about it.
Thank you. Any other questions?
Last question? Thank you so much again.
All right.
Thank you again for...
Thank you all.
Actually, I have a question. Have they ever asked you how to talk like a graph?
Okay, so we are, let me share my screen. We're now at the end. And before you leave, people are leaving, I would like to announce the best paper award for the workshop, which goes to, the Segment Anything model for road network graph extraction. Congratulations to the authors. Are they in the room? No? Okay, well, I'll accept the award. Okay, well, thank you very much, everyone, for attending. We hope to see you again next year. And thank you again to all the speakers and to the presenters and to people who submitted to the workshop. Yes. We are recording and they will be available through the CVPR platform and after 3 months publicly. You're welcome. Okay, thank you again to everyone and see you at the rest of the conference. Thank you.
Thank you.